Call is now being recorded.
In this lecture, we're going to cover the preliminary unit operations used in both surface water and groundwater treatment plants. So we'll talk about screening, primary sedimentation, aeration, and then also adsorption. Adsorption is not as commonly used as these other unit operations, but it is becoming more prevalent, so we'll tie it in at the very end. So first, just a quick review of our typical surface water treatment plant. Again, the preliminary unit operations are our screens and grit chambers and our primary sedimentation, which are both physical processes. And then if we look at our typical groundwater treatment plant, really the only preliminary unit operation is our aeration. Okay, so we're going to talk about each of these and we're going to go through a sample calculation to design a tray aeration system for removal of carbon dioxide. So first physical process for surface water is our screens. Again, these screens are just a physical barrier, okay? We can have either coarse bar racks, which means that there's 75 millimeters between bars, fine traveling racks, which means that the openings are much finer, 10 to 13 millimeter openings. And the whole goal of screens is just to prevent the entry of any debris into the treatment plant. Okay, we want to make sure that we have some sort of physical barrier to prevent any debris that might interfere with subsequent unit operations. So usually these are traveling racks where they just kind of rotate around and are either mechanically screened or just usually some type of cleaning agent applied to the side to make sure that any debris is not getting through and is being disposed of, typically with the sludge that comes out of a settling tank. So primary sedimentation is usually used when you have water that has a lot of turbidity in it, okay? And you have a lot of solids that might be entering your treatment plant. So a primary settling tank, these can be circular or rectangular. And how they work is the water comes in typically, if you're talking about a circular tank, then you have water coming in through the center and being distributed through the entire surface area of our settling tank. Okay. And so there's a couple of important design terms that we should kind of introduce here um, to kind of get a better sense of actually how these particles are settling in this treatment process. Okay, so what's happening in our primary settling tank is that the water is spending some amount of time in the settling tank. Okay, and this is a term that you should recall from the first module. Okay, and that's our theta, and that's our hydraulic detention time. Or sometimes you see it as hydraulic residence time, hydraulic residence, or I'll just call it detention time. Okay, usually a couple of hours. Okay, and this hydraulic residence time is equal to the volume of the tank divided by the flow. Okay, so we set that hydraulic residence time to be long enough so that these particles will settle. Okay, and well, how do we know whether or not these particles are settling? Okay, well, if we think about how this settling tank works, okay, we have these particles coming in to our tank, okay, and these particles are not just going to drop straight down, okay. That's not how it works because our water is continually flowing through this tank. Okay. So when I say that the water spends some time in the tank, okay, that's not entirely true. Okay. We don't ever stop the flow of water in a treatment plant. Okay. However, we just slow it down. Okay. So the water comes into the tank and it's continually flowing out through this decanting trough. But it's slowed down to such a rate where the particles actually have time to settle. And so within this settling tank, if we look at just this settling zone and we just kind of think about it like a rectangle here in our settling zone. Okay. The water is traveling out towards the settling tank, and we want our particles to settle to the bottom. So actually within this settling zone, they are following that diagonal trajectory. Okay. This downward trajectory is our settling velocity, which we call V sub s. And that is the settling velocity of an individual particle. Okay, so maybe in units, centimeters per second. And that settling velocity is kind of in battle with what we call this V sub 0 or our overflow rate. This is also equal to our flow rate divided by the surface area. So if we want our particle to follow this nice trajectory, then our settling velocity should be equal to our overflow rate. Okay. We don't want our settling velocity to be too fast, okay? Because then not all of the particles are going to get removed. Okay. And we don't want our settling velocity to be less than our overflow rate, again, because our particles are not going to be removed. So we don't want our settling velocity to be less than our overflow rate because then our particles won't get removed. If our settling velocity is much greater than our overflow rate, then we've over-designed our tank. Okay, so we need to have this nice balance between our settling velocity and our overflow rate. Okay. And so we will talk more about the relationship between these two terms in our sedimentation lecture, where we will actually fully design a secondary settling tank. The next preliminary unit operation is aeration. Okay. Aeration is primarily accomplished through the use of these tray aerators. Okay. And the whole purpose of aeration is, as the name implies, is just to saturate the water with oxygen. Okay. And we do that because we want to remove some of the major groundwater contaminants that we talked about last lecture. And those contaminants would be our SOCs and our VOCs. We can also precipitate those heavy metals, which I also have written down right here. And another added benefit of aeration is that it can remove another gas, which I mentioned in the last lecture, which is carbon dioxide. Okay. And remember, we need to remove this carbon dioxide because it interferes with our lime soda softening. So again, if we have this lime soda softening process to remove hardness from groundwater, then we can use tray aeration to remove CO2. Okay, so how this tray aeration system works, okay, is usually we'll have multiple trays. So each of these here you can see in this picture down here is a tray. Usually there's some type of material or media like stones or gravel. The raw water comes in, flows over those stones and gravel, and as it does so, it gets oxygenated, and then our aerated water comes out. Okay, so if you're using a tray aerator system to precipitate heavy metals, usually they'll just get stuck back on these stones. Okay, Or you can actually pump oxygen into the tray aerators if you're not using these stones, and that's another way of oxygenating your water. Okay, so we're going to talk about how we design a tray aeration system for the removal of carbon dioxide. Okay, and so this equation is just, it's very simple. So I'll write it down here and then I'll define all of the terms. So C over C0 is e to the minus kn, okay, where C0 is our initial CO2 concentration. C is our final or our effluent CO2 concentration. We have K, which is our gas transfer coefficient. Typically, K values range from 0.28 to 0.37 for CO2, with higher values being for good tray ventilation. And then N is just the number of trays. And it's the number of trays in each aerator. So if we look at this diagram here, okay, and we have our water flowing through, this would be our initial carbon dioxide concentration. This would be our effluent carbon dioxide concentration. And then these are the perforated trays. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 trays. Okay. So you often have multiple tray aerators in a single system, and each tray aerator has a set number of perforated trays. Okay. The perforated trays, the number of trays is really combined with our gas transfer coefficient, is what affects the overall removal of CO2. Okay. So let's walk through an example. Okay. We have a groundwater containing 8 milligrams per liter of carbon dioxide is to be degasified using a multiple tray aerator with 3 trays. Okay. 2 tray aerators in parallel are to be used for flexibility in operation. We have a design population of 5,000 people, maximum day demand of 570 liters per cap per day. We have a K value and we have a hydraulic loading. Okay. So the first step that we need to complete is to determine the carbon dioxide of the water, carbon dioxide content of the water, and then determine the size, the area, length, and width of the trays if the length to width ratio is 2.1. Okay, so a lot of information here. When we don't know where to start, we always start by sketching our system. Okay, so let's do that first. Okay, so we have a groundwater that contains 8 milligrams per liter of CO2. All right, so I'm going to draw my little groundwater well here. This is my groundwater, and this has a CO2 concentration of 8 milligrams per liter. Perfect. Okay. And it's to be degasified using a multiple tray aerator with 3 trays. And we have 2 tray aerators in parallel are to be used for flexibility in operation. Okay, so we have a multiple tray. So each tray aerator has 3 trays, and we have 2 total tray aerators. Okay, so we're pumping out this groundwater here, and it's being split into 2 different tray aerators here. And each tray aerator has 3 trays. So 1, 2, 3, 1, 2, 3, and then comes back out. Okay. 2 tray aerators in parallel to be used for flexibility in operation. The design population is 5,000 people. Okay, so I'm just gonna write down some additional pieces of information here that are probably going to help us. The maximum day demand okay, is 570 liters per person per day. Okay, so maximum demand, 570 liters per day. That cap is per capita. That just means per person, if you haven't seen that term before. Okay. The K value is 0.33. And the hydraulic loading is 400 liters per min per square meter. Okay, great. Okay. So lots of information. And we will start with determining the carbon dioxide content of the water. Okay. So we know the initial carbon dioxide concentration. That is our 8 milligrams per liter. Okay. And we need to know what is our final carbon dioxide concentration. So this is just applying our equation over here. C over C0 is equal to e to the minus kn. Okay. So we have C over C0 equals e to the minus kn. C is our final carbon dioxide concentration. That's what we're looking for. Our initial is 8 milligrams per liter. Our K is 0.33. And then our N is our number of trays. So we have 2 tray aerators, but each tray aerator has 3 trays. So then our N is 3. So then our C ends up being 2.97 milligrams per liter. Okay, first part done. Now we need to determine the size of the trays if the length to width ratio is 2 to 1. Okay, and so we want to determine the overall size of the tray aerators. Okay, we need to get to the area, the length, and the width. Okay, and so the information that we have here is our population. We've got 5,000 people. We've got our maximum day demand, and we have our hydraulic loading. So let's think about what we remember from, units and mass balances, and see if we can use this information to get to our aerator design. Okay. So first we have this maximum demand. Okay. So what we have coming into our tray aerators is our Q max. Okay, that's our maximum demand of our flow. Okay, but this maximum demand here is in liters per person per day. Okay, and we know that our Q, okay, always should be in units of volume over time. Okay, so usually, units of liters per day, meters cubed per second, etc. So fortunately for us, this is a very simple calculation, right? We've got 570 liters per person per day, and we have the population. So we can easily get to that Q max, okay? Just by taking that maximum demand and multiplying it by that population. Our demand, 570 liters per person or per capita per day, times our population, which is 5,000 people, gives us 2.85 times 10 to the 6 liters per day. So that's the total maximum flow that is going to these aerators. But then if we're using both aerators at the same time, which we're going to assume we are because it doesn't tell us otherwise, the flow going to each aerator ends up being split. It's actually Q max over 2. Okay, the total flow is being split, so we've got half the flow going to one aerator, half the flow going to the other aerator. Okay, so we can kind of define this as our Q per aerator is just equal to the Q max divided by 2, okay, or 2 aerators. So it's just half of this, which is 1.43 times 10 to the 6 liters per day per aerator. So I'll just make a note here. This is 2 aerators. Okay. So now we've used this population, we've used this maximum demand, we've used the K, we've used the CO2. The only piece of information we haven't used yet is our hydraulic loading. Okay. And if we look at the units of hydraulic loading, if you've heard this term before, if you haven't heard this term before, we can tell what this hydraulic loading tells us about this system just by looking at the units. Okay, we've got 400 liters per min per square meter. Okay, liters per min we know is just a flow. Okay, but then it's tacked on to that square meters. Okay, so it's a flow rate per area of the aerator. Okay, so our hydraulic loading, we'll call that QL, and that's just equal to our flow divided by the area. So this is very useful information for us because we need to know the area, okay? If we know our flow, which we do, we just figured it out per aerator, we know the hydraulic loading, we can easily solve for the area. Okay, so let's do that now. Okay, so our hydraulic loading is equal to the Q per aerator divided by the total area of the trays. Okay, or just rearranging this, area is equal to the Q per aerator divided by our hydraulic loading. Okay, so our total flow per aerator, we just solved for that. That was 1.43 times 10 to the 6 liters per day per aerator. And then our hydraulic loading, 400 liters per minute per square meter. Okay, and then, of course, because we always have issues with units, we've got a days and we've got a minutes, so let's take care of that. Okay, so we've got 60 minutes per hour, and then 24 hours per day, which takes care of that, which gives us a total area of 2.5 square meters. Okay, so that's the area of our tray aerator, and then we have the length to width ratio of 2 to 1. Okay, so just very simply, our area is just our length times our width. And if the length to width ratio is 2 to 1, then we have 2W times W for our area. Okay. So plug that in, 2.5 meters squared is equal to 2W squared. Then our width ends up being 1.11 meters, and our length is 2.22 meters. So this is how we get to the overall design of our aerator. Okay, so we started by solving for the final CO2 concentration, and then we just used some information about the flow rate, the population, and the hydraulic loading to get to our overall area and then the length and width of our aerators. Okay. So the last preliminary unit operation that I'll just mention briefly here is adsorption. Okay. So adsorption can be used in both surface water or groundwater treatment. And adsorption is really typically employed to remove taste and odor causing compounds. It can also remove discoloration from water. Um, but sometimes if you have a lot of taste and odor causing compounds, um, two of which I mentioned in an earlier lecture, that was geosmin and MIB, those are algae, okay, that contribute to, poor, really earthy, musty smell and a poor taste in your water. So sometimes if you have these, you want to get rid of them right at the beginning of your treatment train. Okay? And you can do adsorption with charcoal. Okay, so this charcoal is what we call activated carbon. Okay, and so activated carbon is just carbon that's been processed to increase the surface area. So when I say process, I mean it's been heated to a really high temperature. And so when you do that, you end up significantly increasing the surface area. So 1 gram of activated carbon, a gram is like a paperclip weight, can have a surface area of 500 square meters. So if it has a very large surface area, there's a lot of places or points on the carbon for these taste and odor compounds to stick to it. Okay, so they adsorb to the surface. Okay, the surface area has slight negative and positive charges, so it can absorb multiple types of contaminants. It can also absorb polar charge compounds. Okay. So this is becoming more widely used as we start to see an increase in these taste and odor compounds in our surface water or in our groundwater. Okay. Adsorption can also remove SOCs and VOCs. They can get stuck onto the activated carbon as well if they have an affinity for it. So again, we talked about the preliminary unit operations, screens, primary settling, aeration with a tray aerator design, and then also adsorption.